Okay, so I think it's a good time to start. Okay, so let me recall where we got last lecture, actually. So we introduced these ribbon graphs. Right? So basically, we got these ribbon graphs by gluing uh, kind of a flower of bands. So gluing bands. So let me do this. So we got the long graph. So but by this I mean the following. For example, we had a vertex of 4 bands, a 4-valent vertex, right? We just 4 bands. And then we glued in some way. We just used some sigma or some gluing. And then we got, in this case, actually, so we got something like this. I mean, so for example, one possibility was this. The other possibility is this. I mean, it's the same thing. So this is a ribbon graph, and this is a band that do. Now, one thing we have to notice, maybe I was not very clear in the last lecture, that different gluings can lead to the same ribbon graphs, right? So we have to be careful. We saw that also in the case of graphs, usual graphs. So, so the one thing to note is that different gluings can, not necessarily always, but can lead to the same optoisomorphism. Same means optoisomorphism. Ribbon graph, right? I mean, so in this case, we didn't do these two things, but here, for example, we can have another gluing, right? So it's a different sigma. So let me maybe draw it over here. We can actually glue these two things together, right? So we just glue these things together. Right? So this thing is isomorphic to this, as ribbon graphs, these are isomorphic to each other. But as gluings, there are different gluings. There are different pairings of this on the set of bands. Gluings or pairings on the set of bands that we have here. Right? But there is one more gluing that's not the same as this. And that was the following. So we just this, right? So, and then we just do this. This is a different ribbon graph. Okay. So in this case, for the 4-valent vertex, we have 3 gluings, but only 2 ribbon graphs. So 3 different gluings. And only 2 different ribbon graphs. Okay.
Mathematically, what kind of objects are these interval graphs? How do we write them in terms of like some sort of sets, maybe?
You mean ribbon graphs?
Yeah, like usual directed graphs are like, but you have a set of vertices, set of edges, and some range and source.
Yeah, they are. Yeah, I don't know if that's your question, but they are actually oriented topological surfaces with boundary.
Not the gluings, but just the graphs themselves.
These are
Yeah, just the same with boundary, like some closed surface, not
no,
closed.
no, no. These are not. These are
Okay.
the result of gluing. The end result of gluing, which I call ribbon graph, is an oriented Riemann surface with boundary.
Okay. And what about the bands?
Well, the bands are basically topologically they are fattening of just these graphs I mean vertices. I mean there is not much difference between this and that, and that's what we used in the case of usual Feynman graphs that in the first part of the lecture we discussed. So this is what the order. Is that
Yeah,
does it answer your question?
yeah, it is. Thanks.
Yeah, so I think I think that's yeah. Okay, so the reason we want to distinguish between them is that actually we will get two different expansions. So again, recall from last lecture that in the last lecture we showed that actually by doing this sort of graphical device of this gluings, we can write a trace of expectation value of trace of H2n is equal to sum n to the power f of sigma over sigma, right? Where this f of sigma is number of faces that you obtain here from the ribbon graph, or number of boundaries, which is the same. F of sigma is number of faces is equal to number of boundaries of the ribbon graph. Of the ribbon. So this is the formula. Now we can write this. Yeah, we have to do double index here, and then you see with the double index, then you see that. And of course, you use Wick's theorem. And and also this formula that the propagator formula. So you see one important formula was this. Remember, Hij, expectation value Hij, HKL is equal to delta IL delta JK. This was very important, among other things. You use this plus Wick to get this sort of result. Okay, but now we can actually expand this this thing as a sum over ribbon graphs instead of gluings. All you have to do is to divide by the symmetry factor, because different gluings can lead to the same ribbon graph. So we have to divide by a symmetry factor. We write the general formula now, but just let me write a little more general before doing that. More generally, this is not the only expectation value you want to compute, because you can have products of traces. Okay, So the best strategy is to group them together depending on the power of H. And then, so you're interested in such expectation values, trace of H to the power of alpha 1, order 1 trace, times trace of H2 to the power of alpha 2, trace of HK to the power of alpha k. Right. And notice these sort of functions cannot be reduced to one trace because there's not a simple relation. This product of traces and trace of products. So trace is not multiplicative. So, but there are this. So this again, we can just write again sigma n, the power f of sigma, again over sigma. Now this time sigma belongs to set of pairings of a disconnected, I mean, not necessarily connected, of a set of bands. So the set of bands are now, we just put for first power, just we put alpha 1 of these things, degree 1 things. And then for example, if there are like 3 of them, I mean, so this is like alpha 3 valent things, alpha 1 valent things, and then maybe alpha 4 valent things, and so on. And then what we do, we just do the glue pairings among these things. So now you have to think these are like bands like this, right? And then you start pairing them together in any which way that's possible. Any which way that. Okay, so for example, here you want to pair these two things. You want to pair this, and so on. All possible pairings that you have. By the same thing, you get that using a Hill mixed theorem, this sort of relation. You get this formula. Yeah. Okay. So now I can write same thing in terms of summing over ribbon graphs. So if you are interested in knowing this, so then we can say star is actually equal to sum over gamma. Yeah. So let me write it completely. So integral over Hn, trace of H, yeah, alpha 1, trace of H2, alpha 2, trace of HK, alpha k, d mu of H, these are the expectation values. Now this is equal to sum over gamma. Yeah, maybe I'll put this outside first. There is alpha 1 factorial, alpha 2 factorial, alpha k factorial. Yeah, and then 1 to the power alpha 1, 1 to the power alpha 2. Oh no, 2 to the power alpha 2, sorry. Up to k to the power alpha k, and then there is sum over gamma, yeah, n to the power f of gamma over order of the automorphism. Yeah. So this is a summation now. Gamma this time belongs to set of isomorphism classes of ribbon graphs. Ribbon graphs, which are again just topological surfaces oriented with boundary with alpha 1 valent vertex, alpha 2 valent vertex, and then alpha k valent vertex. Yeah. So this is exactly like that, but there are much less summands here because there we are we are summing over all gluings. Here we are summing over the results of gluings. And the proof of this is exactly like the proof that we gave in the case of Feynman integrals. We went from gluings of these 2M labels to the graphs that we obtained. And if you remember, we used orbit stabilizer theorem from group theory, which is very simple thing. So proof is exactly the same as the previous one, using this result, and that result also just observation about those things. So, of course, I mean, the challenge with this is to compute this automorphism of this ribbon graphs. That's kind of, it could be tricky. So, yeah. So let me give you one example, which is you find it almost in every text discussed. So, um, so what is that example? Well, I mean, it's exactly here, this example. So I'm going to keep those three pictures there. So I'll just write it here. Yeah. Okay, so yeah. So here's the example. Imagine you want to compute trace of H4. Simplification value, which is nothing but integral trace of H4 d mu of H over Hn, right? Yeah. So we saw that was the sum over gluings for pairings. We got the formula that this is equal to 2n cubed plus n, right? Remember? We have three summands, two of these. I mean, this is n cubed plus n. Because this was the formula that sum n to the power number of bounds. This is just the sum of powers of n. And there are only three things in this case. Now, if we want to do using this formula, or if you want to sum over ribbon graphs, we have only two choices. Huh? One is this, the other one is this. So we have to find the automorphism groups of these things. So the automorphism of this one, I just write it, but I won't spend time to justify that. Maybe you can spend some time to justify this for yourself. Automorphism of this is Z4. It's a cyclic group of 4. It's a group of order 4, so there are only two possibilities, either Z2 cross Z2 or Z4 cross, or just cyclic group of order 4. We have only two groups of order. It's this one. Its order is 4. Automorphism group of this is Z2. So its order is 2. So this formula then tells me that if I want to sum over ribbon graphs, I have only two terms to sum over. One term is 4 times. So this factor here, I get 2 to the power of 2, which is 4. I get 4 times. No, 4 to the power of 1, sorry. 4 to the power of 1. And then I've got n over 4 plus n cubed over 2. This is the order of automorphism group of this one. This is the order of automorphism of the one on the right. And this is the factor that comes from outside. Because, I mean, here we have alpha 4 equal to 4. No, alpha 4 is equal to 1. There's only one 4-valent vertex. So it's 4 to the power of 1. This gives us this coefficient. I mean, already something interesting happens here because we have to write the sum over 3 terms as a sum over 2 terms. This sort of combinatorial factors show. I mean, so there's this sort of, yeah. Okay. Now, we want to go to a kind of dual picture, which is very interesting. So we are now going to sum over actually discretization of the surface. So this is actually it's very much in use. This is alternative graphical device. Discretized or polygonalized surfaces. Discretized. Which by this I mean polygonalized. Surfaces. I mean, there is a mathematical term for this, which I discussed a little bit, but now we discuss it more. This is called maps. So the idea of map is the following. Imagine you have a globe and you have all the countries on the globe. So it partition the globe, surface of a sphere, into these regions. The only thing is that each region is a polygon. It's not like a curvy crazy thing. It's a polygon. We can count how many edges each region has, which is called the degree of that, and how many faces you have, how many vertices you have. That's it. That's the idea of map. So, okay, now how do we go from this, which is a thing drawn on the surface anyhow, it comes with the surface. The surface is itself, to a surface without boundary and this polygonalization. The idea is we go to do all of the so if you have a, say, some yeah, so okay, so actually I'll just do this. Imagine you have a 4 vertex like this, I mean 4 valent vertex like this. You can just choose points in the complementary places here, 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 and connect. Then you get, you can replace this by a square. And we see this as the dual of this 4 vertex. It's the dual here. Or you can have something like this, maybe. A trivalent vertex. You can, again, do the same. You get a triangle. So the dual is going to be the triangle. Okay. So now it's clear. So we have this surface with boundary. We're going to do this for each vertex in the surface. Then you get a decomposition of surface into these polygons. Obviously, these polygons are not going to intersect. They're going to just meet each other on the boundaries, on the edges, and it gives a complete polygonalization of the surface. Okay. Now, what happens? Some interesting dualities happen. So I can list it like this. So let's call these things gamma, which is a ribbon graph. Here we get the surface sigma. I haven't drawn the surface and I haven't drawn the ribbon graph. I just draw one vertex of it, and here is just one piece of the surface. So sigma is the surface, low surface. So the vertices of gamma corresponds to faces of sigma under this duality. Faces of sigma. Edges of gamma. Here, edges correspond to, again, edges over there. Sigma. And faces of gamma. These guys, the complement of the bands, is called, consists of faces. Faces of gamma correspond to vertices of sigma. So if you compute Euler characteristic by either method, you get the same answer. Because chi of sigma, of gamma, is number of vertices minus edges plus faces is equal to F minus P plus V. That's what happens by this. So you get the same Euler characteristic, the same genus. Now there is a little bit of problem here. You may think that, you say, this ribbon graph was a surface with boundary, right? So I have something like this, maybe you would say. Okay, so this has genus 2, has two boundaries. But I can close these boundaries and turn it into a closed surface. And then here I get a closed surface. And the genus does not change if you add these two things at the end, because genus actually, it doesn't change. Actually, genus, you see, Euler characteristic is defined for any topological space, but genus is only defined for closed surfaces without boundary. So we have to do this. But the formula is always the case. It's true. So this is a very nice method because, this is, so such things is called a map, as I said. So the mental picture of a map that we have then is very convenient because, so if you want, for example, genus 0 map, so you have a sphere, and you can actually decompose a sphere into some triangles, for example. You can do that. Right? And there is something in the back, and then. But you don't have to stop at triangles. You can have quadrangles. I mean, whatever you like. But it doesn't even have to be just quadrangles. You can have quadrangles, triangles, and pentagons. The three types of faces. That's quite possible. You can count on these things, etc. So there is some combinatorics involved with this, which I'll get later on. But in terms of counting how many polygonizations are possible, how many different triangulations you have with certain number of triangles, certain number of edges, certain number of vertices. These are very interesting combinatorial problems, but I don't want to discuss it now. But the formula that we have here, we call this formula double star. This gives us something very, it's completely equivalent, but it's nice to write it this way. So there is a theorem. So this paper was written after a paper of truth. So this is by some very famous people. It's basis Itzikson. What is the Zuber? So this paper came out in 1978. It's a very famous paper. So Itzikson, do you remember who is Itzikson? He wrote a very famous book on quantum field theory. He was an excellent mathematical physicist and physicist, amazing guy. Parisi, do you know Parisi? He got Nobel Prize in physics for a spin class theory a lot of things a few years ago. Zuber was excellent physicist. So it's a really good book. So the theorem that they proved by using that result, which is exactly equivalent to that, not using it, is the same. But what they noticed is that they found actually the right scaling here so that the leading term has a limit as n goes to infinity. So that's the crux of this. So the theorem says that the expectation value. So we bring those coefficients to the left-hand side and multiply by that. So we get expectation value of product of 1 over nk factorial, k from 1 to n, then n over t, trace of hk over k to the power nk, zero is equal to sum over maps sigma t to the number of vertices of sigma over order of automorphism group of this map sigma, and then there's times, of course, I have to multiply now by n over t to the power of Euler characteristic. Yeah, this is the part that gives us the Euler characteristic in this. So we are replacing n by n over t essentially. And then, okay, so n over t to Euler characteristic sigma. Yeah. So in this notation, of course, for some function f of h, the invariant function, is by definition, this is nothing but 1 over z0. Now we have to be careful about this. This is integral over hn, exponential of minus n over t, trace of h2 over 2 dh. So we introduced this factor n first of all. We didn't have this n before. But I already discussed the importance of n because that takes care of some normalizations later on. But then there is this factor t, which is very important. This is called 't Hooft parameter. This was introduced also by because we saw something that we are going to discuss soon. But the rest is just in that formula you replace n by n over t and then. So if you look at this, chi sigma is 2 minus 2g. So you can write this as summing over genus, and you see that the first leading term is n squared. The leading term is n squared. So for now, that's And trace of hk over k, it should remind you of something in the ordinary Feynman theorem that for graphs, for Gaussian integrals, summing over graphs I discussed. What was that term over there? We had trace of, not trace, we had some terms like in the expansion, the potential was of the form sigma xk over k factorial. The combinatorial factor was k factorial. But here, the combinatorial factor in the matrix case is k. And this is the right normalization, and k factorial is the right normalization over there. So that's another big observation. I mean, Yeah. If you don't put the scale, then things get quite messy. I mean, because working with bases of gamma is not very convenient. It's better to work with something which is topological. And Euler characteristic is topological, but phase is not topological. That's only 1/3 of the Euler characteristic. So this is the, so by this device, the whole thing can be written in terms of a topological expansion. And this really is essentially is Hooft. I mean, yeah, 1974. But this guy used it, did a lot of amazing thing that one of them we'll discuss today. Yeah. Okay. So actually now indeed we want to discuss what they did using this expansion. So we go back to these integrals. Yeah. So yeah, we want to discuss now quartic integrals. So back to quartic matrix integrals. I mean matrix models. In fact, we are interested in, as we discussed, we can just sum over connected graphs or connected surfaces, which means we take log. So we just take log of integral over hn exponential of minus n over t is here. Yeah, I just say trace of h2 over 2 plus, yeah, trace of, actually, I don't put n yet. Just, so this is a bit, now the notation is a bit jumbled, sorry. So this is minus t trace of h4. So let me just, yeah, so t trace of h4. Mu of h. Okay, let's just use this. Yeah. But we have to switch to this normalization. Okay, so this is now a something new because it's really a quartic potential, like anharmonic quantum oscillator. There's H4, and here is of course H2, which is the Gaussian free part. Okay, so the goal is that after rescaling, we want to show that this actually, the leading part can be computed. So the goal is to compute the planar leading of, yeah. Actually, it's better to consider as I was writing. So minus t over n, yeah. Yeah, this one, this is better, the mu of h. Yeah, right. So here, I just erased it. but there's Euler characteristic. The Euler characteristic is 2 minus 2g. So it starts at 2 and then goes to 0, negative 2. So this is the n powers, right? So it decreases. So if I want to get a chance of computing the limit as n goes to infinity, I better divide by n squared. If you divide by n squared, then the leading term is free of n. So then we take this 1 over n squared log of integral, the free energy integral over Hn, exponential of minus t over n, place of h4 in mu of h. This we can just write as E0 of t plus 1 over n squared. E1 of t plus 1 over n4 E2 of t so this is the planar part, genus 0. No, genus 0, Euler characteristic 2. And basically what we're going to show, we cannot compute this, but we can compute the limit of this as n goes to infinity. And that's the larger limit. So the limit of this story the n goes to infinity. We're going to see that we can compute. And as I said, we are going to use two things. One is orthogonal polynomial technology that we developed, this generalized Hermite polynomials, together with topological expansion. So we put these two things, we fuse the two things together. So, so this is the question is, what is this limit? And so idea is use Hermite polynomials plus topological expansion. So we have already done some work with Hermite polynomials. I mean, generalized Hermite polynomials. I mean, it's not a question of Hermite itself. It's a generalized for quartic potentials. So let's now see what we have got. Okay. Any question from the audience? Is there any question? Okay. All right. So recall I mean, we had some polynomials. I'm not going to put anything. So these are like pk lambda k from 0 to infinity. So it's a generalized Hermite polis. One crucial property that they had was that there's a recursion relation between them. So lambda pk is equal to pk plus 1 plus rk. Yeah, pk minus 1, right. But this rk are some numerical constants belonging to R. Yeah, they are not very long. So this is a recursive relation that allows us to compute pk plus 1 from these things, but we have to know rk. That's not a trivial matter. I mean, this is a very difficult problem to compute these things because you see, this is not like Hermite polynomials. This is a quartic potential. It's much more complicated. Okay, and then we derive, so this is from the couple of lectures ago, we derive this relation that k is equal to, yeah, rk. We derive some recursion for these numbers of k's. So k is equal to rk plus 4t. Yeah, rk times rk plus 1 is a very, yeah, rk plus 1 plus rk plus rk minus 1 star, and he said this is this discrete Pandolay equation 1. This is discrete Pandolay. Yeah. Okay, so now we have to sub it because we are not working with this is there's something t over 10. Yeah, we factor that. So subbing t over n for t because we're working with that new constant. So in t over n for t in a star. Yeah. And divide by n. We get this relation that k over n is equal to rk. Yeah, we get k over n. You divide by n, we get k over n, rk t times 1 plus 4t times rk plus 1 t plus rk t plus rk minus 1 t. So we call this double star, where this rk is rk divided by n. Little rk equal to rk divided by n. So I have yeah. Okay. So now here is something very crucial happens now. We can let n go to infinity. If you just let n go to infinity and don't change this parameter t actually, or k actually, you don't get anything. So we want to let n go to infinity and k go to infinity in such a way that k over n remains equal to some constant x. or at least approaches to X. So let me write this idea here, which is very important idea. This is called double scaling limit. So double scaling limit. We let n go to infinity. And yeah, you let also k go to infinity. Such that they go to infinity at the same rate, basically, such that k over n, yeah, goes to x. You see, k is always less than n. So it goes to x belonging to this interval 0, 1. Yeah. Okay. Then double star implies that x satisfies the equation. X is equal to, yeah, r times 1 plus. You see, here is 3 times 4, we get 12t r. So it goes to 12tr. Yeah, x is equal to r times 1 plus 12tr. Where, as I said, r is a parameter that depends on two things, x and t, which is the actually limit of r of x and n. T divided by n. That's n goes to infinity. Yeah. So what do you want to do now? So right. So yeah. Oh yeah. Now I derive an equation for r of 1 and t. So let alpha of t equal to r of 1 and t. So if we put x equal to 1 here, r of 1 and t. Now this is equal to, you just solve this equation. If you put x equal to 1, you can solve this for r in terms of t. You get this equation that you have a quadratic equation, you solve it, you get equal to minus 1 plus root 1 plus 48t quadratic formula divided by 2040. This equation, if x is 1, you can solve r in terms of t. It's a quadratic formula, you get this. Right? But this thing we have seen before, this quantity. Do you remember where we have seen this? We have seen it when we were proving the Wigner semicircular law. This is the generating function for Catalan numbers, essentially. So this is the generating function. for Catalan numbers. So let me write it down and then let's see what it is. So this is equal to minus, essentially, I mean, there's some factors that creeps in, but that's same. So this is equal to actually sum, yeah, minus 1 to the n, right, 12t power n times c. Yeah, I mean, I had t and cn in the thing, and the equation quadratic thing I derived for t and c, but it's 12t, but that's the same. Yeah, and because I see. So, yeah, Catalan numbers, yeah. Yeah. So now you guess that something very interesting could happen because those Catalan numbers we met when we were computing the moments of trace of H2K or H2M in respect to the Gaussian measure, which is free, no potential. Potential was equal to 0. Now we see that when we introduce a quartic potential, at least for the leading term, also these Catalan numbers show their head somehow. So this is kind of perturbation of that result that we had for the free theory. This is a non-free theory. Okay, so for now that's enough, but we'll see more of this. So then take log of, I mean, that's what we have, that the computed integral of Hn exponential of minus t trace of H4 d mu of H which we already shown that this is equal to Cn. I mean, this Cn has nothing to do with this Cn, by the way. This is Catalan number. This is a constant from the theory. So maybe I'll call this cat n actually. Here is cat n. Yeah. So this is Cn n factorial. Yeah, this was the final formula that we obtained using the generalized orthogonal polynomial Cn n factorial, R1 to the n minus 1, R2 to the n minus 2, and then Rn minus 1, the 1. Then there was this factor H0 to. So if we just take log of this, which is equal to that, and do the new normalization T over N, so we get 1 over N squared. Yeah, log of integral over Hn. Yeah, exponential of minus T over N, trace of H4 d mu of H is equal to minus 1 over T sum k equal to 1 to N, 1 minus k over N, log of Rk T divided by Rk0 minus log of. Yeah, k0 of t or 0 of t. Yeah, divided by or 0 of 0. Yeah. I mean, you take logs and then you reassemble them like this. That's not difficult. So this is, but this is the Riemann sum for an integral. So as n goes to infinity, I can write this as an integral. This is the Riemann sum for an integral, this whole thing. Right hand side. This is the Riemann sum. Yeah, this integral. Yeah. So this we call the left hand side. Okay, now we have to. So this thing I called it E0, but no, I want to. Yeah, this limit of this thing. So let me call limit of left hand side as n goes to infinity is E0 of t, which is equal to now this integral that represents that, which is minus integral 0 to 1 minus x, this is 1 minus x, log of, yeah, r of x and t over x dx. This so this is our notation for E0. So yeah, E0 is the planar part of the thing because this was the when you expand, when you take the limit, you reach the plane part first. The only part that you have access to the plane. Okay. So yeah, so what we can do then that basically that's more or less the end of the calculation because so replace x in terms of r using this equation that we have over the so the equation that we use is of course x is equal to r times 1 plus 12t. And this gives you that E0 of t, that expression is equal to, yeah, integral from 0 out of t. Yeah, I can just express this here 1 minus r minus 12 tr. Yeah, 1 plus 24 tr. Okay, yeah, log of 1 plus 12t. I mean, you can compute this integral. This is calculus problem, and that's turns out to be equal to actually minus 1/2 log of total. Yeah, plus 1/24 1 minus alpha times alpha minus 9. So alpha of t, as before, I introduce alpha of t is equal to r of 1 and t, x equal to 1, which is, we have over there, minus 1 plus root 1 plus 48 t over, 24 t. And so finally, you obtain a series for E0 of t. So we obtain. So this was our goal, that we wanted to obtain a formula for E0 of t. And in fact, E0 of t is equal to, because we wrote the expansion of this term in terms of Catalan numbers. There was a power series that we derived. You just sum it into this equation, and then you have to take log of this, perturb it in terms of the series in t. That's not difficult. You do. Now, actually, you can give all that to some mathematical, to your AI favorite AI. Will give you the answer in a second. So the thing that you get is actually the following: minus sigma, and from 1 to infinity. Minus 12. Okay. T, I believe. No. Okay, so I just put 12 to the power n, then times nth Catalan number over 2n times n plus 2. Yeah. Right. 2n. Yeah, okay. So this is the end of this part of calculation. But then can you tell me if this series is convergent or divergent for any t? Because we spend so much time deriving it, but is it convergent or divergent?
My guess is divergent everywhere.
Sorry?
Divergent everywhere.
Except, of course, for t equal to 0, right?
Yeah.
Yeah, that's correct. It's
Because the
divergent.
Catalan, sorry.
Huh?
Because the Catalan numbers grow way faster than
That's right.
anything that's there.
Yes, absolutely true. Yes. Indeed, this is divergent for all t different from 0, because Catalan numbers grow exponentially. Not grow at, not factorially, but definitely exponentially. This goes. So there's no way you can find a t that makes this conversion. So we obtained a divergent series. So what? What is the importance of this divergent series, you might ask? Well, each term computes some combinatorial information in terms of number of maps on Riemann surfaces of certain genus. So I will not elaborate on that yet, but I will say that we'll see that each term computes a number of maps of certain types. I believe it's going to be with n 4-valent vertices, labeled n 4-valent vertices, and certain number of Yeah, I think N for so this is a very difficult combinatorial problem that can be approached purely combinatorially, but it's very difficult. But by these methods, so this guy. So again, there is an account of all of this. If you want to read, go to book Lando Zvonkin. You can also read the accounting book of Einard, Counting Services. Einard, Counting Services. Or you can use, you can go to original paper of versus E6 on parentheses of the original paper. At least this is the source of your okay. So I was thinking because something very strange happened here, very interesting happened here. And that's this idea of double scaling limit. I was thinking maybe I spent a few minutes in one context, which is much easier than this, explain to you what this double scaling limit entails. Okay, so let me. Yeah, I think it's good to understand this in a much simpler context. Yeah, let me. Yeah. Much simpler example, double scaling. So you consider a binomial random variable or distribution, binomial NP, where P is probability of success, say between 0 and 1, and N is something. So this is the probability of, so let me put it like this. Probability of X equal to K is equal to N choose K e to the K, 1 minus P to the N minus K for all K less than or equal to N greater than or equal to 0, and it's 0 everywhere else. So this is the famous binomial distribution, right? Which is the result of flipping coin n times and measuring what is the probability of getting K heads, for example. If the probability of getting head in one try is P. Right? So we have two parameters here to deal with. One is N, the other one is P. So first limit is which we usually study is we keep P fixed. And then let N go to infinity. We do that. I mean, if you look at this, the distribution of this thing, so the mean value of this random variable mu is NP, right? And the standard deviation, you remember what is the standard deviation? We can compute it, but the standard deviation is NP times 1 minus P, I believe. Do you confirm?
Yeah.
Huh?
Yeah.
Is NP times 1 minus P. So it's a bit problematic to say what is the limit of X as a probability distribution as n goes to infinity, because it's like a moving target, because I mean, here is 0 and here is n, so you have all these things, but I mean, here is the mean is np. It peaks here and then goes down. So it's almost like a normal distribution, but the mean is moving and this thing is also moving. But you can take care of that by subtracting, by centralizing it. So what we can do is the following. You can center it. So we can just say a lim of x minus np divided by the standard deviation, which is np times 1 minus p. Now, this is pretty good because this always has mean 0 and standard deviation 1. So for that, I believe I have to divide by this. Probably. Yeah. Now, this converges to normal, standard normal distribution with mean 0 and deviation, standard deviation 1. So this is a standard normal. Standard normal distribution. Okay. So that's the case where the probability of success doesn't change, right? It's kept fixed. But then so this is like a random walk. We repeat this infinite number of times, and then we want to see that it's approximated somehow. But there is another possibility. We can let n go to infinity and p go to 0 in such a way that the product is constant. So, and that's a very simple double scaling limit, which is like this. So, alternatively, they double scaling. So we let n go to infinity. But then the probability of success becomes very small. So this is the probability of rare events, very rare. P goes to 0 such that np goes to lambda. Well, lambda is a fixed number between 0 this. Not 0, not even, just. So then in this case, the question is there a limit to this?
That
Obviously.
more of the Poisson distribution since
Yes.
lambda.
Excellent. Yeah, exactly. That's the Poisson distribution, where the probability of 2 consecutive events approaches 0, but you let there be many trials. Yeah, exactly. In this case, this X converges to Poisson. Poisson. Lambda. So maybe I'll call it Poisson lambda. So probability of Poisson lambda. Now, in this case, of course, it can take any integer values, including 0. Poisson value is equal to k. Is equal to eta minus lambda to the k over k factor. for K is equal to 0, 1, 2. And somehow when you're introduced with Poisson distribution, you wonder what's the point of this and how can I identify some natural examples Poisson things. Indeed, it's a bit, for me, at least it's complicated to understand when some trial is Poisson. But using this sort of, maybe makes a little more sense, I don't know. Yeah. So it's a double scaling limit. It's not one of them. And in the case that we did, it's much more complicated. Okay, I think we are good for now. From Monday, actually, we can start climbing Mount Hariri Zagir, Har Zagir. This is the Everest. So this is the computing orbifold Euler characteristic of modular space-long curves. What we use, we won't need this. We just need the orthogonal polynomial technology. But some nice topological ideas. So this I did to show a little bit of kind of things that goes in the direction of Parisi, H6 and Zuber paper. So, but you can read much more in. I may still get involved with. Actually, on Monday I may get involved with this. Yeah, so because these models show phase transitions for certain value of the parameter, and we want to see what happens at those phase transition points. So I may discuss that. That's also some discussion in Landau's Rankin, and we'll see Pandové equation emerging. The actual KDV hierarchy emerging in that picture. So that's maybe I'll do that. Yeah. Okay, well, thank you so much. So, are there any questions? Yeah, thanks. So I just say goodbye then. Have a great day. See you on Monday.